Let's get started. Hi, I'm Shivram, and today I'm going to talk to you about SparkR, a project that enables interactive data science at scale on your Hadoop clusters. I'm a PhD student in the AMP lab at UC Berkeley, and this is joint work with Zhongheng. So to start with, let's take a look at the two software projects that are part of the name, which is Spark and R. I guess most of you must be familiar with the term, with the Spark project right now, but for those who aren't, Spark is a general-purpose distributed query processing system, which is very fast. But not only is it fast, it also has other nice properties. It's very scalable, so there have been a lot of performance benchmarks which show how performance improves with scale as you add more and more machines. And it's also very flexible in the sense that Spark can, say, process your input data from either HDFS or HBase, run on Mesos or Yarn, and easily perform transformations or operations on them. And it's a very concise form to express your analytics jobs. So the transformations could be things like running a map or a filter operation, which is the map is similar to a map function in, like, say, MapReduce. And these transformations give you back another RDD. So you start from an RDD of string, you apply a map function, you get back another RDD of string. There's another set of operations which are called actions, which actually take your RDD and materialize something out of it. So let's say you run count, you get the number of elements in the RDD, and you can see that in your interactive shell, for example. Or you can also save your RDD into the HDFS using something like save as text file. So this distributed or parallel collection API is very powerful, and it's also very general purpose. And there was a talk actually just in the previous session which shows how you could unify different programming paradigms using this kind of an API. So why is this API actually good for writing R programs? I mean, R is this very flexible, and like it's a language with a lot of properties. How are we going to write R programs using this API? So it turns out that R is actually very, very well fit for this task. And to motivate this, here's a quote from the R user mailing list, like where people ask questions about how to do something using R. And questions usually go like, how do I use a loop to do blah? And the answer typically is don't, because loops are terribly inefficient and in an interpreted language, especially like R. And the answer to most of those questions is to use these apply functions that come out of the box with R. These apply functions, for those who are not familiar with, are similar to like a map function in Spark's API or a map function in MapReduce. All you're saying is that I have a list, and I want to apply a function to every element of the list. So instead of writing a loop where you call the function, you instead declaratively say, I want to apply this function over all the elements of the list. So our programmers are already used to and are already trained to actually use these kind of apply functions to express their computations over collections of data. So there's sort of a natural fit between taking the RDD abstraction and taking the distributed a collection abstraction in R and putting them together. So we did that. We wanted to put R together with RDD. What would we get? We could get an R2D2. Well, but we didn't quite do that. We instead said we could take an R and RDD and get RRDD. So what's special about the RRDD? The RRDD is this class in R, or a package in R, that exposes a large number of functions that you can use to operate on it. This includes all of the things in the Spark API that I showed you 2 slides back. But it also includes some new functions which provide an R flavor to your jobs. So for example, we support lapply on this distributed collection. So you could similarly use your same functions that you were running on local lists, and you could just run them on a cluster now on a distributed list. There are also some Spark-specific functions, like, say, broadcast or include package. And I'll walk through how these functions are useful and why they're very easy to use in the next few slides. So if you're introducing new programming API, it's sort of traditional, I guess, these days to start with word count, so we will start there. I'm showing an example of how you can use SparkR to do word count on your file, which is stored in HDFS. The first line here is just opening the file in HDFS. So SC is the Spark context object that you get when you start R shell or when you include the package. And we're reading it and saving it into an RRDD called lines. So having gotten lines, we can now start operating on these RDD using the API functions that I talked about before. So the first thing I do here is that I split the line by space, and I get words out of it using this flat map function. Following that, I have a list of words, and I use lapply on it. And remember, this is an lapply on the cluster. It's not a local lapply that's running. And I just add the number 1 next to each word so that I can do the aggregation. So the last 2 steps are doing this aggregation, where we take the word count RDD that we created, and we reduce it by key, and we apply the addition operator. So there are a couple of nice things about this line of code here. So one is that we are able to use R's inbuilt addition function, which is just this plus in quotes that you see there. And that automatically adds integers or vectors or matrices out of the box. And the second thing is, when you run this, it actually kicks off like Spark jobs, which actually compute this for you. And you might notice that you can actually refer to all of the any external keyword or any function inside these closures that you pass around, and SparkR automatically serializes them, ships them across the cluster, and performs computations using them. The final step here is we collect the word counts that we created to a local machine, to the shell, and you can then print it out or display it and so on. So this was a simple demo. It's been done in all sorts of frameworks before. So we want to do something a little bit more exciting. So we're going to do a bigger demo right now. And this demo, just before we start, let me just sort of outline what we're going to do here. So what we're going to do here is we're going to start with this MNIST handwriting data set, which is a collection of images which look something like what's shown in the slide here. There are a bunch of zeros, a bunch of ones, and so on. And the task here, the machine learning task here, is to identify what is the number in each image. Right? So this is a well-studied challenge, and there's been like decades worth of research into how to improve algorithms to do this, and so on. What we're going to do today is we're going to start with raw images, and we're actually going to train a model so that we can then test it and predict what number is there in each image. Right? So to do that, we're going to do 2 broad steps. So the first step is going to be converting these images, which are like JPEG or PNG images, into features, which are vectors or array of doubles. Right? And we're going to use a specific featureization process to do this. And at the end of the featureization, we essentially get these 2 matrices, like A and B, that are shown here, except these are distributed matrices that are spread out across the cluster. Following that, we're actually going to do the training phase, which is going to compute this model. And we're going to do that by minimizing a loss function. And the loss function we're minimizing is this least squares loss function. That's AX minus B, the 2 norm of AX minus B. And to compute that, we're going to use the most direct way to do it, which is a closed form solution for computing this model. And that's going to give us the value of X. So let's switch now to the demo, and let's see if it all works. OK, so I've got one machine running on EC2. It's a small data set, so it's just a small representative demo. You can run Spark on multiple machines. So there are enough like tutorials to tell you how to do that. And what I'm using here is I'm using RStudio, which is this IDE for R that's very flexible to use. So I'm running RStudio on that EC2 machine, and I'm just connecting to that using my browser out here. So I'm going to start off this job, which is going to do the training of the model, and then I'm going to like walk through pieces of the code to actually explain what's going on here. Okay. So there are different windows here. The top one is like the editor, and the bottom one is the console, where things are actually running. I'm just going to minimize the console for now while we look at the code. So to start with, we include the package. So this line is very key. We want to include SparkR, okay, before we start doing anything. And it's just a normal package similar to other packages that you use in R, and there's nothing special about it. And once we do that, the first thing that you typically do is to create a Spark context, which is SC. And to do that, here I'm using 8 cores in my local machine. So I just say local 8 to create the Spark context. But you can also pass in a Spark master URL, like which is on Yarn or whatever, you know. So following that, we want to read in our input data. And I've created this data file here, which is train MNIST-dense. And I read that, and I create 8 partitions out of it, which is the same as the number of cores I have, so that I can like do parallel processing. So this stuff seems pretty reasonable. The next step is to actually do the featureization, like parse the data and do the featureization. And to do this, we use this notion of random features. This too much, I don't have too much time to go into details of why we do these things. But the big idea here is that we have these matrices, these random matrices that we're going to multiply our data with in order to get the features out of it. Right? The next stuff, which is actually very interesting, is these lines 16 and 17. So what we're going to do here is we're going to use these matrices W and B in all of the processes that we are running, in all of the parts of the data that we are processing. So we broadcast them so that we don't have to serialize W and B each time we start a task. So this broadcast will create copies of W and B on each machine, and whenever you want to use them, you don't need to actually send them over again and again. So it's a performance optimization. And line 19 here is basically saying we're going to use this matrix package in our job so that we know that SparkR knows that it should include this package before running any computation. So this is actually very powerful and flexible. So any third-party R package that you're using, you can include it as a part of your closure by just this single directive saying include package. So now let's go to the actual program where interesting things are happening. So the first step is we just read the matrix. So we have, it's a CSV file of RGB values that I start with here. So I have a function to read it, which is called read matrix. And following that, we actually do the featureization. And another nice point to note here is we cache the features that we're creating. And what this means is that the features will be stored in memory. So that when we're doing the A transpose A and the A transpose B that was on the slides before, we actually don't need to recompute the features each time. Right? So we create the features, again, using these kind of lapply-like functions. And now we're ready to actually create our matrices A transpose A and A transpose B. So to do that, this is just a parallel computation where we take the output from the previous stage. We transpose each matrix locally, and we multiply it. This is just our syntax to transpose and multiply matrices, and you can naturally use that. And we then collect the results from each part of the cluster, and we add the output to get the overall value of A transpose A. We similarly do something for A transpose B. So now let's see if our job ran. It actually did finish successfully. And the nice thing is you can still use the Spark Web UI to monitor, to see what's going on, and so on. So we cached one RDD, right? I mean, so what happened to it, there were 8 partitions. It was 417 MB. It's cached in memory. So all of the Spark utilities that you use today should still work with this as well. So now let's go back. Let's see how good the model that we learned was, OK? And to do that, there's a test data set, which is 10,000 more images, which we're going to try to predict stuff on. And we're going to compute what is the error that we get. So I just kicked off stuff to do that. And while this runs, the big idea here is that in the test data set, we have these known values that we actually know the labels that we have for them. And we're going to compute what is the error rate on it. And we get around 6% error rate here. This is a reasonably high error rate, actually, for this problem. But we ran a really, really simple algorithm to do this out here. So, and it's still pretty reasonable. So computing the error rate is something you can still do using a lot of other languages and frameworks and so on. The part that is cool about using R comes in this bit where we can say visualize where we made these errors. So to do that, I've plotted this thing called a confusion matrix. Whoops. How do I? All right. So this is a confusion matrix that I plotted, which is what was the actual label that was there, and what was the label that we predicted. And this is sort of a heat map showing where did our predictions go in. So the diagonal is where we want to be at. So we want the diagonal to be all black and everything else to be all white, which means we have 100% accuracy. So we can see interesting things like, for example, 7 and 9, we seem to confuse a lot. So there's this region or this box here, which is on top, which is we say it's 7 when it's actually 9, right? So you can actually figure out where is the algorithm making mistakes by actually visualizing the output that you get using existing R packages. So this was just one line of code that I wrote to do that. You can also do more fun things. So you can actually see the images that we got wrong. So let's see this. So this was an image that we expected it to be 4, but we got 1. It kind of looks like a 1, I guess. And we can do more of this. So here's another one, which it's expected to be 9, but we got 1 again instead. So this is just a small example of showing how you can, say, debug your algorithm, or you can visualize what your algorithm has done, because now we've combined these two paradigms which let you do your visualization and things of that sort using R, but you can still do your parallel computation using Spark. All right, so let's go back now and go to the third part of this talk, which is how does this all work, right? And to do that, I'm going to give you first a high-level picture of the data flow that goes on in sort of a job, for example, in the job that we just ran. So there are 3 boxes here. The first one represents like your driver or your local machine from where you launch the job, right, or your R shell or R studio and so on. And there are worker machines which are actually doing the computation. It's similar to a name node versus data node kind of like separation of concerns. So on the local machine where you launch R, when you say R on your command line, we launch a process, you get R. And when you include SparkR, it loads a bunch of R libraries associated with it. And specifically, when you create a new Spark context, what it does is it creates a Java Spark context associated with it using a small JNI binding. And this helps us get a grip into running Spark jobs using this Java Spark context. So when you actually run a job, like when you say count or reduce by key or something like that, the Java Spark context is used to talk to these Spark executors, which will then execute the query on each machine. Note that because we are dealing with user-defined functions in R, each worker spawns R and runs the computation out there, and then gets back the output and passes it back to the Spark context. Right? So I'm going to specifically focus on 2 parts of this diagram. First, I'm going to look at what's inside the orange pipe, or what goes on between the Java Spark context and the executors. And specifically, this is very interesting because of this automatic closure serialization that we do. So for example, if you refer to a variable outside the scope of your function, SparkR needs to automatically capture that variable and make it available on all of those worker machines that were there in the last slide. So to do that, we make use of the way R is set up, and it's specifically its environment structure. So what we do is, just a small primer on how R sets up like variable scoping, is that there are a list of environments that are associated with every R session. And the environment contains a bunch of variables and functions and all other objects like that. And these environments are sort of nested in the sense that for every environment, you have a link to a parent environment. And so what we do here is that when the user submits a job to us, we actually traverse these list of environments that we have, and we capture all of the variables that are being used by functions that are that is being called. So this lets us automatically capture anything that you want and put it together in one big blob that can be shipped across to like a worker machine. There's still a little bit more detail which is key, which is that how do you get this one big blob out of these list of functions and variables that you have? So we again use R's like functionality to do this. And I guess if you've used R, you've already run into this where when you try to quit R, it asks you, do you want to save your session, right? And you have a yes or no answer. And when you hit yes, what it does is it actually serializes everything that was in your session and saves it to a local file. So we use the same functionality to actually save all these variables that are being referenced in closures. And then instead of just saving it to a local file, we ship that across the network so that it can be loaded on the worker machines as well. So just by using our structural properties of environments and also based on its existing serialization formats, we're able to get this very nice feature of having like closures auto-serialize themselves. So the second part that I'm going to talk about is how do these R workers, Spark workers talk to R on these worker machines. And, and specifically, I'm going to talk about this notion of having a pipeline RDD. So going back to the word count example, if you have 2 operations, like say flatmap and lapply, one natural way to do this might be to say from Spark, you launch R, you run flatmap, then you come back, and you again launch R, and you run lapply. But this becomes inefficient very fast. And this is because in Spark, typically your lineage or like the list of functions you run is long. It's like 5 or 10 functions. And you need to launch R each time in order to execute this. And there's a lot of process launching overhead and data transfer overhead. So to do this, we introduced this notion called pipeline RDD, where we coalesce these functions that are going to run. And we call R exactly once. And we run the coalesce function inside R. And we come back to the Spark executor. So this helps us handle even long lineages of 5 or 10 function calls by just launching R once and running all of those 5, 10 functions that are required and coming back to the executor. So a little bit about the status of SparkR. We have an alpha developer release, which is available on GitHub. There's a one-line install command, which is very nice. And the dependencies are not too much. So you should try this out. You can just try this out on your laptop, actually. You don't need a big cluster to try this out. And in terms of implementation, the high-level design is very similar to the Python frontend for Spark, like PySpark, which exists. And the basic thing that we learned during this process is that Spark is actually very easy to extend. So we just added around 300 lines of Scala code, which was the R RDD class that I talked about before. But most of our work was in writing R code for the API, which was around 1,700 lines of code. More significantly, we wrote like 549 lines of test code to make sure all of the API functions behave correctly. And that's been very helpful. There's more stuff in the GitHub repository. There's scripts that help you launch EC2 clusters and set up SparkR and things like that. All of the examples that ship with Spark, we've ported them to SparkR as well. And you can take a look at them to see how to implement things. And also the MNIST demo that I just showed you before, the handwriting recognition one, that's also available. And the data set is on S3, so it's like sort of public, and you can play around with it. And finally, we also have instructions on how to build with your own Hadoop 2 flavor or use Maven and so on. However, this is still a very young project. I mean, the alpha developer release went out in like mid-January or February, and there are a number of things which are still in the pipeline. First, we are looking at a more higher-level API. Data frames are very popular in R, and it's for good reason, because they make it much more simpler to use and do high-level operations. And we're looking at, can we provide a more distributed data frame like API? We're also working on integrating SparkR with the other Spark libraries like GraphX or MLlib and so on. So you should be able to launch a k-means or a logistic regression application which runs on a cluster using just one line of R code. And finally, we're also adding support for reading from other data sources. This is a little tricky because of needing to produce exact Java classes for sequence files and HBase input formats. But this is work in progress right now. So just to summarize, today I talked about SparkR, which takes this notion of RDDs and extends it to a notion of distributed lists that you can program using R. And the two key features that make it very useful are that it automatically serializes closures and lets you reuse existing R packages in order to perform distributed computations. And at a high level, the goal of this project is to combine the scalability that you get from Spark and the utility that you get from R and try to provide a unified environment. Just again, this is the GitHub repository URL, and you can send me an email, or even better, you can post to the Spark user mailing list, and that's pretty active, and we get back to you pretty soon. With that, I'll take any questions.
If you have any questions, I'll bring you the mic. Just raise your hand, please.
Hi. So I have one question that if the model, what I need to execute is not fundamentally additive in nature, like say SVN or maximum entropy, then will this architecture work where you partition the data and then, because they're not additive in nature, right?
Yeah, so that's a good question. It depends on the model that you're working with. So if you have a linear loss function, it's very easy to make it additive, right? If you have a nonlinear loss function, you can still make it additive using like gradient methods, for example. So if you have a logistic loss or an SVM hinge loss that you're dealing with, you can use gradient descent instead of using a closed form-like solution. And you can compute the gradients in parallel and then aggregate the gradients as you want and try to update your model based on that.
So in that case, the aggregation will still happen in the main controller node?
Yeah, the aggregation happens in the main controller node. But because the assumption is the model is small enough that it fits on your controller node. Yeah.
So eventually, say, if I'm implementing this in a Hadoop cluster, so I can elect any particular data node as a controller node to do
Yeah,
that?
you can choose any node as a controller node. Yeah.
Okay, I have another small question. So what is essentially then would be the difference from doing this using Spark versus, say MapReduce, apart from performance?
So this is not quite the right venue. There was a Spark talk earlier where this question was probably more appropriate. I think there are a long list of differences or similarities between Spark and MapReduce. I mean, some of the in-memory caching stuff might be useful, especially when you're training models. Also, you could use some of the existing higher-level API. Like, you don't need to rewrite logistic regression. You can call Spark's machine learning libraries logistic regression. But we can talk more about this as well after the talk.
Hold on, just.
So I have a question about the reduce part, the collect that is basically collecting. Is it like a streaming collect, or is it because R usually has memory issues if the data is too much? So is it like streaming the data and then processing by that, or does it require to have all the data in the reduce section?
Yeah, that's a great question. So is the collect a streaming collect versus this thing? So I think there are two versions of it that I went through. So one is there's a reduce version, which is a little bit like streaming, where you get one partition. And let's say you're doing add, it just adds in place in that partition. The collect, however, does require all of it to need to fit in memory. Because what it's doing is it's getting every partition and doing like a R bind, or like it's just concatenating rows or columns of the matrix, for example. It's concatenating rows in this case.
And then with that, do you have some statistics of how large would that scale basically,
So it depends. So collect is something that we don't typically advise users to directly do unless you're very confident that it's going to be a small data set that's coming at the end of it. I mean, if you just read your input data file and did collect, it will crash. I mean, yeah, it's inevitable. There are some high-level functions that we're trying to add. So for example, you can already find the length of the data set. And there are also like size estimator functions that we're looking to add. So you get an idea of how big an RDD is before calling collect. But that's very good feedback.
Any more questions? Raise your hand. All right, well,
All right,
that's the
thank you.
end of our presentation. Thank you.